As Karen said, my name is Corey Kell. I'm the creator of Flat Earth Intel. And basically, this briefing to you is going to be a knowledge and information share. Something, I've talked to some people here already, and one of the gentlemen said, I've seen everything from on Flat Earth. And I'm like, yeah, you ain't seen this yet. So. Again, thanks so much to the community, and it's great to see everybody here this morning. A little bit about my background information. Who's Corey Kell? In other words, who's this individual that's standing in front of me trying to tell me that the earth is flat? Okay, now a lot of you have already come to that conclusion. Do we have anybody outside the continental United States, Oconus? Everybody within the continental United States? Okay. A little bit about my biographic information. As Karen said, I was in the military. I was in the United States Army Field Artillery for 23 years. I retired in 2006, and I did all facets and all job functions within artillery. Tactical trainer advisor. I'm a certified master gunner. I've also done the survey and celestial survey operations. After my retirement in 2006, I went right into defense contracting, which a lot of military does. A lot of the military folks, just because the jobs are there and you have the technical training and expertise. I've been in defense contracting for 15 years and came back from Afghanistan this last year. But I've done all sorts of jobs within that field: communications, combat trainer, team leader, technical trainer. In 2017, I started work on a project on a defense contractor handbook, which now came out in 2020 by Syllabus Publishing, and it's basically the 101 of defense contracting. Where it all started for me, how I got into Flat Earth. And really, I'm not a Bible beater by any means of the standard. I was raised a Christian by my parents. But my interest in giants led me to Flat Earth. As I looked on the internet, I was doing research on the internet. It kept telling me, hey, check out Flat Earth. It kept recommending me in right around 2016, 15. When I first heard this subject, I laughed at it and I said, wow, Flat Earth, people really think the earth is flat? That's crazy. So as I continued to do my research, I found a different story, and I finally looked at it. And what I ran into, I did the research, I went into and looked at Mark Sargent's Flat Earth's Clues, and that started me on my journey. So then that raised questions within myself. And I thought, there's something, that I know within the military field of military science, using the sun and geometry, that I can provide solid evidence that the earth is flat. So I started to do my research, and there's a lot of great content on the internet. You should be very proud of yourself, those creators who are putting out that excellent content on the internet. Give yourself a hand. So, with that, using the sun, and the reason I say we use the sun, and this is my message to you, it's the real answer. The sun is the gold standard. The military uses it. They use it for celestial survey operations. It is definitive and it is absolute. We can also use military science and geometry to determine the sun's actual distance. And a lot of this information is out there, but you have to really search. It's in a lot of different little corners on the internet and in books. But we can use the sun by measuring direct sun angle, get down our timing to determine what we're really living on, what the surface shape of the earth is, and the sun's actual distance between 3,000 or 4,000 miles, whether it's a physical or projected object. Right now it seems to be a projected object. And one thing I want you to remember, and that is the sun is always 90 degrees to a person, place, or thing every second of every minute of every day of every year within the prime meridian zone. Once you fully understand that, that is the end of heliocentrism. What I'm talking about is the high sun. In other words, there are times of the day that the sun is too high in the sky for you to observe it from a curved surface, okay? You just have to know when and what sun seasons. So this is what I've put together on the website, and I encourage you, if you have questions about this after my presentation, please feel free to come up and talk to me. I'm a very open person. And that is, some of the considerations, we need to understand timing. Timing is critical. In other words, what time of day is the sun too high in the sky? And what I'm going to talk about is putting in a sun survey point, something that eludes the heliocentrists. They don't like it because it's timing. Once you put in a sun survey point, that sun comes right back to that survey point the following day. You cannot escape it. What we also need to understand, the observer location. In other words, where we're observing the sun. And the real difference is beyond 45 degrees. At 45 degrees and below, during certain times of the day, it's indistinguishable. In other words, both the heliocentric and geocentric model would work. But once that sun gets above 46 degrees, she's flat. It is only flat. We just need to identify that. And by times, I'm talking about between the hours of 9 and 10 a.m. in the morning and 3 and 4 p.m. in the afternoon. The sun seasons, I'm talking about late spring, the summer sun, and early fall. Higher altitude gives you lower sun angle. Sea level will give you the highest sun angle. Sea level is the closest to the geometric perfect form of the Earth's shape. And I use this example. It's like a two-story home, okay? If you're in a two-story home and you see that at a certain time of the day, in the morning time from 9 to 10 a.m., if that sun's in the first window, in other words, at a low angle, it's indistinguishable. You could be either coming from a flat or curved surface. But if that sun appears in the second window from 9 a.m. and 10 a.m. in the morning, and then the afternoon from 3 to 4 p.m., you're on a flat surface. That sun is too high in the sky. And I'm going to talk about how do we determine that. In other words, I understand what you're talking about. Now, how do I determine that? And we're going to use military science and a little geometry. This is kind of the intro. Again, using the high sun, using the sun to determine what we live on. This is the agenda for this morning's briefing. I'm going to talk a little bit about the history of flat Earth, equations versus reality, and experimentation. As I did my research, that's one thing that I saw, and I saw the heliocentrists like to use math. They like to use equations versus reality and experimentation. We're going to talk about the types of observation, whether it's a solo observation. I'll use the term, you'll hear me use the word STO, which is solo timed observation, which is a single observer, or we can do multiple observers, a simultaneous or simo observation. We're going to talk a little bit about the types of protractors to use and how we operate those, and a little bit of geometry. I know everybody's favorite subject, right? Math. I only like to know math when I see money in my account, right? How do we test the models? In other words, we're going to do a test, and we're going to apply the results to both models. In other words, how do we test the globe model, and how do we test the flat Earth model to determine what our surface shape is? And that's something I'm going to lay out for you. The orienting station, or the OS, what type of equipment, and how we set it up. Very easy to do. The 9-step geometric validation process. In other words, this is something we should have been taught in our education, but we weren't. We were shown pictures, movies, NASA moonshots, okay? But when I asked a heliocentrist, what's your validation process to determine Earth's true surface shape? They show you snappy. Right here, somebody told me it's spherical. Yeah, but how do you determine that? So we're going to talk about that. That's not a validation process. I'm going to talk about the military science of it all. Something that the gentleman made the comment, I've seen it all. You ain't seen military science, baby. I'm going to show you how it all sinks in. And I'm going to tie in visual perspective. And I'm going to tie it in, as you note, there's some really great examples of visual perspective. Rob Skiba did one, and Dave Weiss did another one here recently with his son. So we're going to talk a little bit about that. Operation Resolute Time 2020. If you're a flat earther, this should be in your vocabulary. What is it? It is one of the most extensive tests on the sun done in recent history. Measuring sun angle. I've did it in a combat zone in Kabul, Afghanistan. During a 6-month period of time, over 80 tests. We're going to talk a little bit more about that. That should be in your vocabulary if you're a flat earther. And then I'm going to talk a little bit about the complete operating system, what we may actually live in. With that, let's get started. Equation versus reality and experimentation. And really, the heliocentric model is kind of brought on to us by Nicholas Copernicus. And he kind of starts it out. Now, there was some stuff a little bit earlier with the Greeks, but however, Copernicus, that's where they really, the heliocentrists really tried to bring that model within reality. However, all of science wasn't in agreement with that. And you had people like Samuel Robotham Bedford, who did the Bedford level experiment in 1838, 1839. And that experiment proved that you could see behind the curve, basically. Now, the heliocentrist had a lot to do, there was a big argument about that experiment. And they recreated that experiment and said, look, you can't see the flag down that canal. In other words, heliocentrists, some of them are very clever, and they will use weather and conditions to benefit their model. And that was the same thing happened with the Salton Sea experiment. How many of you remember that? That was kind of a fiasco. Yeah, the heliocentrist will do that. And this is one of the reasons that I created what I've created. I'm talking about going above 10 to 15 degrees above the horizon, because from there we can exclude atmospheric lensing and refraction. The military does it all the time. I'm going to show you how. Michelson-Morley came out in 1887, and the heliocentric model said, hey, we've got the Earth is moving, it's rotating within a solar system around the sun. Well, they wanted to prove it, but they got the wrong answer. They got a null reading. They got in trouble, and it was like, wow, we proved the other. So in comes a man named Einstein, brings in the theory of relativity. If we can't visually prove it, what are we going to use? Math. We're going to use equations. So I'm going to give you a 10-minute equation and tell you that's what you live on. See, check out the equation, and I'm going to give you an example of that. So Einstein comes up with a theory of relativity. And basically what Einstein did is he removed the ether. And ether, if you don't know what ether is, it's kind of like, I'll give you an example. If you're standing next to a pond with no wind, and that pond is like a glass mirror, you take a stone and you throw that into the pond, it creates a ripple effect. Okay? That's evidence or movement. Ether does the same thing. If there's anything moving within the ether, you're going to get that ripple effect. Okay? All Einstein did was take the ether out of the equation. All science, I said, wasn't in agreement. George Sagnac comes out in 1914, does basically same experiment as Michelson-Morley. Now the ether exists. It's there. Gets basically the same result. So that science proved that the Earth wasn't moving. There was a huge problem. So what's the next solution? We've got a problem. People aren't going to buy the heliocentric model. So what do? What's the next best thing? You give them fantasy. I'm going to give you fantasy in movies. I'm going to try and open your mind up, and I'm going to just shower you with science fiction. And probably one of the most significant events in history is the advent of science fiction in 1926. Hugo Gernsback starts it off. Whether this was with intentional or unintentional, it had an effect, and it benefited the heliocentrists. Look at the huge science fiction realm of movies that we have now. It's huge. And you look at the sci-fi community, it's huge. So fantasy is the other factor that the heliocentrists use to their advantage, and they use it every day. We just need to be aware of it. I put Nikola Tesla up here because Tesla saw what was going on. Tesla said, hey, you guys are building a structure up in the sky that you're using mathematical equations that have no relation to reality. In other words, they built a grid up in the sky using equations, and that's where they formulated their model. Thank you. So that's where they formulated their equations. What happens is they run into a problem because the heliocentrists have to use geometric or geometry diagrams, and that gets them into trouble because equations go away from geometry. You have to show geometry in your diagram, but they don't use geometry. Matter of fact, they avoid it like the plague. One thing I found out in my research is that protractors, heliocentrists do not like them. They do not like to use them. Now you'll see a photo of a mechanical protractor in the Copernicus photo I showed you, but they do not like to use mechanical and manual protractors. Why? Because it shows angle. And once you show angle, you can do what? Triangulation. Military does it all the time. And it gets them in trouble. So one thing I found is protractors to heliocentrists are like crosses, holy water, and garlic to vampires. They hate them. They do not like protractors. And I'll give you an example. I was on one of the chat boards. It's called Q-Aura, and I don't know if any of you have heard it. And it's full of heliocentrists. And I call them, there are a lot of what I call intermediate heliocentrists. A lot of good mathematicians. They know how to do equations. And they'll use those equations, and they'll try and tell you, hey, I cannot see how the Earth can be flat using this equation. Yeah, that's a nice-looking equation. But what are they using? They're using a geometric diagram. You got a problem. Because now geometry and equations are going different directions. But you need to know how to identify that, and you can use it against them. Matter of fact, you can decimate the heliocentric model. The heliocentrists come out, and I've heard some people say, yeah, you know, both models work. We can prove it. Really? Yeah. The geocentric model is just philosophy. Really? That's interesting. So what if I told you that we can prove the heliocentric model is false? Whoa, what are you talking about? Yeah. Your shit's off. And it's off by quite a bit. But you have to take the time. Heliocentrists have called me a very technical person. I can see you're a very technical person, Corey. You're damn right I am. I've had to. So, comes up with this equation. And I said, okay, we're using the North Star. Now, what the heliocentrists don't know is you put in a guide angle. Military uses this all the time. You put in a 90-degree angle. Now I'm going to start to use triangulation. I said, that's a nice equation. And I sent back, I said, well, that's 90 degrees. Now, I need some information requirements because I want to see if you actually did the experiment. You're going to tell me that the Earth is flat just based on the equation. You're not going to impress me. You don't have anything, you don't have any evidence. You've got an equation. And I said, nice equation. Now let's fill in the real information. There are some subtle hints in the sun diagram I've provided. And I copied and pasted back. And I said, there's a big difference between chalkboard equations and reality. In other words, here's the requirements to solve your diagram. And I already know that he didn't do the experiment. I said the actual known distance between stations. Latitude, what's the latitude of your stations at? Instrument, what device are you using to measurement? Time of your observation. Station height from Earth's surface, you made the measurements, 0.5 meter, 1 meter. What was the distance? The composite angle calculation, surface angle of the observer, in other words, how the observer is oriented, and the actual measured angle to the object. Diagram shows triangulation. What is the object's true distance? Because you can do it. Once the heliocentrists put up a geometric diagram, you fall within geometry. And that's a big problem for them. They don't like it. So in this sun diagram, I said, for one, you're going to have a problem. He tried to tell me that, okay, this is Cuba, and this is Canada. I said, okay, from Canada, Cuba, you might be all right with this angle, just based on distance. You might fall within the lines of parallel, and I'll talk a little bit more about geometric angles, but basically all you have is two parallel lines. You can determine distance off an object, whether it's actually true or false, whether that object exists. You can verify it. Line of parallel will tell you that. I said you're going to have a problem, though, when you come into Canada. The North Star sits pretty high up in the sky. He said, well, I'm at 46 degrees. I said, or 44 degrees here. I said, well, you're going to have a problem because the North Star sits pretty high up in the sky. Line of parallel is 46 degrees. I guarantee it's sitting higher than that from Canada. So I said, you're going to have an issue right there. I said, well, you need to define your terms. Right away, they get mad. I don't know what you're talking about. Yeah, you probably haven't learned it. You learn math, but you didn't learn how to do experiments. The flat model, I said, and I will reiterate, the flat model, no matter your distance, all measured angles are 90 degrees or less. Off a flat surface, you can make that because your guide angle is 90 degrees, so it doesn't matter. Now, what you will run into, the heliocentric or globe model, they're going to have a problem because they have line of parallel, and it will kick them in the ass all the time. I said, you're going to have a problem. So that's just an example. That's what we run into on the chat boards on the internet, and I know a lot of you have probably seen the same thing out there. So when I got into and I thought, okay, there's something how am I going to basically do this process? There's a process and application within military science that I know that I can break it down into an experiment. In other words, experiment considerations, the process and applications using the sun, some geometry, and military science. Easy to do. Anyone can perform it down to the 5th grade level education. Why do I say 5th grade level? Because that's when students are introduced to geometry. And really all you need is basic geometry to figure it out. Inexpensive, keep the cost down. In other words, yeah, we want you to be able to do an experiment, but let's not break the bank doing it. Let's keep it under $200-300, and you can do that. Very inexpensive. Test or experiment anywhere in the world. It can be done. We just need to know or identify the key factors: location, longitude, timing, and the sun seasons. We need to know those and the effects, the cause. Types of observation. Stow, which is a single observer, or solo times observation, or SIMO, multiple observers. And basically all those observations are, they're timed observations of an object of reference by a single or multiple observers through visual lines of orientation, whether you're doing SIMO or stow. Same thing. You're just doing a visual line of orientation and measuring it. You're measuring angle to the sun. Types of protractor. You see here before you the manual and the digital, and really high tech has exposed the heliocentric model. The digital protractor, some of them call them angle finders, like this one, are very easy to use. They're very easy to use. This model here runs off a 9-volt battery, and all you do is basically point at the object and click, make sure it's level, and you're going to get your measurement to that object, measuring center mass. We need to know a little bit about geometry. In other words, there are 3 angles we need to know a little bit about in understanding it, and this is very basic stuff. But a lot of it, we're not taught this in our education system. We're taught some geometric fundamentals, but we're not taught a line of parallel, for one. The measured angle. Basically, all the measured angle is a measured angle can be visual, mechanical, or manual. It's something that you're pointing at and measuring just simply by using the protractor, whether it's visual or otherwise. Example, a 45 degree going into a 90 degree. Lines of parallel, where 2 lines, visual or otherwise, run side by side, okay? One generally would be the guide angle. As you can see here, these are vertical lines of parallel. They run 90 degrees. Now, do lines of parallel always have to run 90 degrees? No. They can be in any direction. They can be vertical, horizontal, or any angle in between. Lines of parallel. And I'll talk a little bit more about it because some people get a little bit confused when I say line of parallel. The guide angle, that's kind of like the flagpole angle. The most important angle to an object, elevated or otherwise. Generally, this angle is at 90 degrees. Does it have to be? No. Okay? And is key in performing triangulation to determine measured angle, distance, separation, and line of parallel to an object. Pretty basic. These are just some examples. I mean, you can look at, and these are measured angles. You'll note that the farthest we go away from an elevated object, what we're showing here is the sun, that our angle decreases. This is another thing that the heliocentrist, when I talked to him, he said, I didn't know that. I said, yeah, the closer you get to an object, the higher angle you're going to get. Now, whether or not he's telling the truth, I don't know, but it's pretty basic, pretty simple. And this is the reason I use manual protractor. It kills them, using geometry. Lines of parallel, probably the hardest thing for people to understand, but line of parallel is really an increment of measurement. In other words, within the field of military science, there is a high degree, a high standard of validation within the field of military science. Lines of parallel are accountability. So when I talk about that, one thing I noticed within the heliocentrism and the heliocentric model, they lack accountability. Not only do they lack accountability, but they lack validation in their process and application. And that's huge. Military science, however, does just the opposite. Why? Because lives depend on it. So, lines of parallel, you're the expert. How many of you walked through the door when you came in? Everybody should raise their hand, right? Unless you came in through the ceiling, right? You performed an act of line of parallel. In other words, you just told me you understand line of parallel. Try walking through the wall. Ain't going nowhere, are you? You hit the side of a doorpost. Guess where a doorpost is? It's line of parallel. When you look through a window, when you drove here, you looked through your front windshield, you understood line of parallel. Now, if you're upright and you're looking through the windshield of your car, and you're looking out, try driving your car with your seat reclined all the way back. See how well that works. The observer angle has changed, okay? And that's what I'm talking about, the observer angle. It really affects the heliocentric model and the standard. You're the expert. You do line of parallel more than 50 times a day. If you're touching your touchpad on your phone, your computer, you understand line of parallel. They are both vertical and horizontal in an angle between. Lines of parallel are just that. They can be increments of measurement, such as in a ruler, measuring cup, okay, even a doorway. These are all examples of line of parallel. They are definitive and absolute. Now, we've just did what? We've created accountability and validation, because we're going to use line of parallel against the heliocentric model, something they don't like. You do it every day. It's in your life. Exceeding lines of parallel, like this example here, train on a railroad tracks, when you exceed line of parallel, there are consequences. In other words, like a train derailing off a railroad track, they've exceeded the lines of parallel. They went off the railroad tracks. Those railroad tracks are what? Lines of parallel. You got to follow it. Physics also works against the heliocentrist. But we need to be able to identify how that works. And again, understanding lines of parallel, you do it every day, and there are consequences to it. Enough of geometry for a little bit. If your head isn't tight yet, it may be in a little bit, all right? I know some of you are like, wow. Okay, so let's talk about the models. How do we test the models? In other words, I didn't learn this in my education. How do I actually do a test of the models? And some of you are doing some good tests, visual, lower elevation. And that's good. Keeps the pressure on the heliocentrists. I say, hey, keep them moving. You guys got them scrambling. You got Neil deGrasse Tyson so scared, he runs up and drops a hammer and says, "This is gravity, bitch." No shit, Sherlock. Doesn't mean your surface is spherical, all right? So how do we test those models? Let's talk about that. So what I've developed is a test box. In other words, we're going to break those models down into a 45-degree sector. So we're going to test long distances of the globe and the flat Earth model. We can break it down. What I have before you here is what's called the test box. In other words, we're going to, the center test box, we're going to use the sun from orienting station, whether it's from one observer or two observers, and we're going to measure sun angle, easterly or westerly. Okay? Now, you'll note that there are red dotted lines. What are these? Oh, you get an A. Look at that. Woohoo! All right. See, that wasn't so hard. There's line of parallel, man. I know it. If I learned anything, I learned line of parallel. Yeah. All right. So you'll see here we have the sun, and it's timed. In 3 hours' time, we're going to measure sun angle from our sun survey point. Our sun survey point is going to be put in at a certain time of day when the sun is 90 degrees to us. How do we do that? I got to know how to do that. We can do it, and I'll show you how. It's easy. Piece of cake. So all we're going to do from that sun survey point, we're going to measure 3 hours from that sun survey time, and we're going to measure direct sun angle from our orienting station. Once we do that, we can start to determine whether we're taking that reading from a flat surface or a curved surface. So if that measurement is 45 degrees and below, indistinguishable. But if it's 46 or more, we've got problems. That's a flat surface. Sun's too high in the sky. Let's talk about the test box for each model, the flat Earth and the globe. And basically you'll see a series of two numbers within the test box. The bottom number is the observer angle. All right, the observer angle, what the observer is angled or oriented to the sun at 3 hours. So in the globe model, the observer is oriented 45 degrees. Now I know some heliocenters say, well, you know, it's not a perfect sphere. Well, guess what? If it ain't, that's the best case scenario. Because if it's not a perfect sphere, you're in bigger trouble. Because your angle is only going to increase. How you figure that? Geometry, dude. You ought to try it. All right, so at 3 hours, the observer on the globe model is 45 degrees. Okay, we need to remember that. Observer orientation. The top number is the maximum measured angle to the sun from that observer. That's the maximum number. You'll note that both these numbers equal what? What's 45 and 45? 90 degrees. What did we have as a guide angle in our example? Man, y'all are all over it this morning. Great, that's great. 90 degrees. 90 degrees is the maximum, that is the standard. The flat earth model, now you notice a difference. We got what as the observer angle? 0 degrees, right? How come it's 0 degrees? I'm on a flat surface. It's flat. What's my top number? Man, I got a whole 90 degrees to work with, measured sun angle. Guess who's got the advantage? Flat Earth. Hey, heliocentrists, they'll complain about that. Well, you know, that's not a fair test. Hey, dude, you chose a sphere, not me. No, I'm just going to tell you how to test it. Break it down geometrically. You pick that model. You pick that winner. That's your horse. You got to ride him to the finish. Okay, the test box, the globe. All right, so they're telling us that the sun, the Earth rotates around the sun. Okay, here's how we break it down. 45 degrees. This is the 45-degree sector test box. In other words, I want you to remember 3, 4, 5. 3 hours equals 45 degrees. You are oriented 45 degrees from the time of survey after 3 hours. There are 8 sectors within the globe model. 8 times 3 is what? 24 hours. Guess what happens when you put that sun survey point 24 hours later? Guess where Mr. Sun shows up? Right at the survey point. That's something else they don't like. They're like, man, let's stay on the survey point. I never heard of that. What is that? FE test box, flat Earth. Basically, the sun moves over the flat surface of the Earth. Pretty simple, really. We just break it down. It's 45 degrees, like a pizza. All right, so now we got the same thing. 3 hours equals 45 degrees. Put our sun survey point in, same standard. The only problem is, if you look here, this is the advantage. I got a full 90 degrees to work with. And that's a heavy advantage. But again, it's the model you chose. You chose a sphere as one of the hardest geometric forms to validate. This is how it works against them. Don't let this diagram confuse you. It's a pretty busy slide. You'll see it on the website. And you see here, when we look at, represents the Earth and the Sun, you'll see that the black arrows represent line of parallel. This is our survey point. Our measured angle, we can come from our measured angle either way. Okay, we have one observer or 2 observers, SIMO or STO. And all we're doing is, the red arrow represents 45 degrees. Could be either flat or a curved surface. But once you go beyond 45, you go to 46 degrees, you do the math. The measured angle over here, 46-degree angle, 45-degree curve or surface, 91 degrees. You now exceeded that by 1 degree. This is how far off line of survey the heliocentric model is once you put the survey point in, the sun survey point. Whoa, guess what? Accountability and validation come around and kick you in the ass. Now you're going to tell me you created a grid up in the sky and that's accurate? Don't think so, partner. Think you, if I wouldn't let you in charge of my bank account because I ain't going to have any money left. All right? So at 1 degree, You're 1,638,000 and some change off line of survey. Line of survey works both ways, both vertical and horizontal and vertical. And that's what really gets this model. We can look at their data, the sun, the heliocentric, whether you're 91, 92, 93, or 94 million miles, it's going to work against you. Their model uses distance, and that's their Achilles. And you can decimate the heliocentric model if you know how. You can also disprove it. Now, there's going to be heliocentrics say, well, you can't disprove it. Sure you can. Just use geometry. You just need to know how. Military science does it every day. Every day. They're using celestial survey, line of parallel, weapons bore sighting. They do it every day. It's because military science has a high standard of accountability and validation within the processes. Okay? Can I exceed line of parallel? Heliocentric model right at about 90.3. In other words, I'll give you sun width, about 0.3. I'll give you that. I'll give you a half a degree. Still ain't gonna make it. You ain't gonna make it. That's how far off survey you are. That's at 1 degree. As you increase those angles, as you increase this angle going this way, your ship is sinking deeper and deeper. You're gonna get in trouble. This is line of parallel. In 2019, I went to the Flat Earth International Conference in Dallas, Texas. How many were there? Great conference, wasn't it? It was an awesome conference. I even saw a guy, they say he's with ISIS X, that guy that was on the intro. Saw him there. He was running around. We both got interviewed by a team that was called Live Through Productions. He did an interview before me. And I talked to Live Through Productions because I wanted to talk to some people about this at the conference. I just started working on it. And I said, hey, I just wanted to talk to some folks about this. And I made a handout. So they came up and interviewed me initially in the main conference room. And the guy said, hey, I'm interested in this. Could we talk more about it with you? And I said, sure. So we'd like to do an interview. And I said, sure, we can do that. Just let me know when. Because I talked about line of parallel. And this is really what gets the heliocentrists in trouble with their model. And it really disproves the globe. People will tell you different, but it's just geometry. And it's applied geometry. So what I did is when I sat down and did the interview, there was a 3-person team. Shelley was the coordinator. Alec was the lead. And then Quinn, funny guy wearing a white hat, he was doing the interview, and when I sat down with him, he looked at me and he gave me a funny look, and he said, hey man, I got to tell you, this is the best I've seen yet on flat Earth. I said, well, I'm just getting started, but I wanted to talk to some folks about it. He said, this is really good. So I said, yeah, it's within the field of military science, and it's not out there. The information isn't out there. Some people understand line of parallel, but it's not brought up in our education system, and it really is the validation within to validate these models, to check them out, to see whether they're correct. Let's talk about the orienting station equipment. How are we going to set up? What equipment do we need? Very basic equipment. And here you have, all this equipment can be had for $200, somewhere around, depending on how much you want to spend on a compass, some of the other items. Basically what I've used a dry erase board, 9x13. And here you'll see I've taped the digital protractor. I tape it because during windy conditions, you'll have that digital protractor try and wobble on you a little bit. So if you tape it down, it helps you hold it down during windy conditions. So the dry erase pad is the actual platform. That serves dual purpose. You can write on that whiteboard your measurements, your information. The Neotech digital protractor is attached to it, and that's what you're going to measure your sun angle. Tape measure, you're going to use a tape measure to measure your height, your station height. And I do measurements at a ½ meter. You can do a ½ meter or 1 meter. You just need to know the difference and what effect will happen when you elevate that platform up. The sun shield, and also you need sunglasses. I use double protection. Anytime you're viewing the sun, you want to have coated lenses and a sun shield for your eye protection. Dry erase marker, again, just for recording right on the whiteboard. The other thing is a plumb bob, and if you're not familiar with a plumb bob, all it is you're keeping your station plumb over the sun survey point, and I'll show you that in a little bit. You can check that. You want to be within about a 1 inch from the survey point. The plumb bob helps you align that. The tri-level, this is all it does is you put this on the platform, check for level. The Neotech also has a level vial in it as well. You want to make sure that your station is level. Just increases accuracy. Aluminum stake is used to mark the survey point, or you can use a bottle cap. Bottle cap works good. Single level vial. This is for what I'm going to talk about is the Marx Device. You check cross level on the Marx Device, and I'll show you in a little bit. The lensatic compass, you're going to use this to measure the azimuth to the sun. When you took your sun angle reading, and all you have to do is stand back, just shoot an azimuth to it, just for record, for documentation. And then, of course, last but not least, the tripod. That holds up the whole device. Additional items, like I said, we're going to talk about the Marx Device. I use a stabilizer board, and then, of course, double eye pro sunglasses anytime you're looking at the sun. Protect your eyes. It's a digital protractor by Neotech. Range is anywhere from 0 to 225 degrees, high tech. It's most advanced. Push button system. All you do is basically you're viewing down this top rail, just like you would if you've sighted in with a weapon or you're aiming something. You can practice with it and aim, make targets and do your practice before you actually do the observation. You're just looking right down that top rail. And of course it's all push button. It runs by a 9-volt battery. I checked the accuracy. It says within plus or minus a half a degree. When I checked it with a manual protractor, I wrote out an angle, no difference. It was 0 degrees. So there was no difference. And you want to do that anytime you do testing. This is the Marx Device. This is a sun survey positioning device, okay? Why is that important? In other words, we need to set the geometric edge. And this is when you hear the heliocentrists talk about their little fairy tale stories like, what is it, Aristophanes, sticks and shadows. I keep hearing that. It's like, dude, if you can't figure out a mathematician just put that out there and they put it out there, they never did that experiment. I'll put money on it. I don't believe that for one bit. I said, that's a mathematicians getting together. I don't think that they've ever did that experiment. I said, for one thing, it's done wrong. But I won't get into that. It's all geometrics. It's a very poor example of an experiment. Why? You didn't set the geometric edge, dude. How are you going to measure angle and you're going to use shadow angle? Wrong answer, dude. Wrong process, wrong application. Wrong, wrong, wrong. That's as wrong as doing a U-turn in a circle, traffic circle, all right? And it's just like you hear that and then you think, dude, these people are educated that are saying this? I just shake my head. I'm like, sticks and shadows, really? Even the military figured that out. We use it for direction only. All right, so all this is a 18 by 24 inch piece of wood with a center hole cutting in the middle, and now you use screws or nails, and then you elevate a string line. Now that string line is going to cast a shadow from the sun. The sun's going to cast a shadow. You are going to orient this device, the Marx Device, north-south, using a compass from your location. You can do it from anywhere in the world. Once you do that, you have set the geometric edge. You have set the line. You're now on the line of magnetic. When the sun casts a shadow center line, you now have correct and proper Earth to Sun alignment. Something else that the heliocentrists, I'm not going to use the French word, but they mess up. And they mess, you look at them, it's like, dude, how did you set the edge, the geometric edge? I don't know what you're talking about. Okay, gotcha. All right, so you have to set the geometric edge. Again, it's accountability. The heliocentrists lack it. They lack it in their process. I'm not saying they're bad at math. They're good at equations, but that's about it. Because once they get into, you start to get in experiments with them, you lose them. All right, so now we know how to get proper Earth to Sun alignment using the Marx Device. That's going to put in our sun survey point. We're going to mark it, and then that's where we're going to set up our orienting station. There's a little bit of story behind the Marx Device. I was working with Latvian Special Forces in Kabul, Afghanistan, and the first sergeant came over to me and he said, I see you out here looking at the sun, what are you doing? I said, I'm checking Earth's surface to see whether it's flat or curved. And he said, well, what's the big difference? Who cares whether it's flat or curved? And I said, I said, you know, if you come home from work every night and you're arguing with your wife or your spouse, your kids come up and kick you in the shin, your dog bites you in the leg, probably still going to have a bad day. But if somebody's getting paid billions of dollars every year to tell you something that you don't actually live on, and they keep telling you, then there's a problem, right? He said, yeah, that is kind of messed up. And I said, I have this idea. I said, because I was using an elevated string line off of tripods, I said, I have this idea. I want to build the device using some wood. He said, you know what? He said, come on over to the shop. We got tools. He said, we got the wood. He said, I'll help you build it. And I said, all right, sounds good. And off we went to make the Marx Device. And I said, I'm going to name this after you. He said, all right, good deal. So that's a story behind the Marx Device. This is what I'm talking about. This is the elevated view as you look up to the sun. And this is the line of magnetic. This is when you have proper Earth to sun alignment. This is the correct alignment. And this is put in, this is what the line of magnetic. You are on compass. This is set in with a compass. And again, like I said, I was using tripod, but I wanted to do this experiment to give perspective, to look up and say, okay, this is what it actually looks like. And this is important. You're setting the geometric edge. Now you can start to take your angle readings. And the sun to this orienting station, or where I did this, was 765 miles north of the northernmost prime meridian, or the Tropic of Cancer. All right, so you can see the sun here is where? It's to the south. It's to the south. This is all the Marx Device does. What it does is you orient it north-south, and then you look over here on the right side, you can see that sun shadow right down the center. And then you want to mark that. You mark your time. Your time could be at noon, could be at 1300, could be at 1 p.m. Wherever your location, you can't always get noon at your locations based on where you're at in the world. So your survey time might be 1:45. All right? But it's where, and this is how you transfer, that sun being 90 degrees in the tropics, in the prime meridian zone. All you're doing is transferring survey right here. And you can do that. Bet you didn't know that, huh? Yeah. It's like, wow. All right. It's just military science. All right? This is what you're doing. And this is, again, this works against the heliocentric, and it works hard against the sphere. In other words, you're creating a grid square, a grid pattern in the sky. When you look at the sun, remember, you're always measuring center mass to the sun. You are looking center mass to it. So you have to be within 45 degrees when you're coming off your surface at the designated time. Once you start to go outside that survey point pins you to that survey point, the observer. You can't come off it for your model. Once you come off it, you start separation. In other words, the sun is too high in the sky. You've exceeded your model's standard. And this is what you see, these little dotted lines, they create crosses. This is the grid pattern you're creating in the sky when you do that. So when you go out here, for example, at 46 degrees, you're now 91 degrees. You've exceeded the model's standard, the heliocentric model. Big problem for them. Big, big problem. And it only gets worse as you increase angle. And this is the line of survey. You're pinned. You're pinned to it. And this is what the Marx Device and the digital protractor do. Let's talk about the orienting station setup, the OS, what I call the OS. And basically it's comprised of a tripod, platform, base, stabilizer board, and digital protractor. first step, and all this information, again, you can view on the website. The first step is, I use a stabilizer board because you can shift your whole device using the stabilizer board a lot easier. And you'll see here, you see the blue bottle cap, that's the sun survey point. And what you want to do is, if it's your first reading, after you put the survey point, it's going to be a westerly reading. It's going to be at anywhere between 15 and 1600 or 3 or 4 p.m. in the afternoon. So all you can do is you can use a compass, or you can just aim this right at the sun. Aim it right at the sun as it's going away from you. Again, that's your sun survey point. Put that stabilizer board. Then you're going to put your tripod, you're going to connect it to your platform and your digital protractor. I keep mine connected, so it's a relatively fast setup. You can do this, once you practice it, you can get it down to 2-3 minutes. Starting out, it's probably going to take you about 10 or 15 minutes just to mess around with it. But you can get it down to 2-3 minutes. You can do this really quick, very rapid. What you're going to do is then you're going to level your platform using your tri-level. Once you level your platform, and you also have a level on the digital protractor, you're going to measure your station height. And again, you can kind of keep this close to your survey point. Always keep close to your survey point, the radial arm right here, because that's where you're going to take your measurement from. Whether it happens to be a ½ meter, or you can do 1 meter measurement test. You use a tape measure to do that, get your correct station height, and then you're going to check your plumb, and this is your plumb line. And this goes right over the sun survey marker. You just put that right over your sun survey. You want to be within about 1 inch. This practice is directly from military science, astrological survey operations, directly. It is solid, it is fundamental in principles and application. Once you do that, you've got your station. You want to check record your GPS location, your elevation, because elevation has a lot to do with it, so you need to know your elevation. And we'll talk a little bit more about that later. So you record all your data. You can either do your GPS or your longitude. And then record that. You can record it on your whiteboard if you want, or a marker and pen. I like using the whiteboard. This is what it looks like. So this is the actual observation. So the one on the left, this is a side view, and you can kind of look along the side of the digital protractor if you want. This is that top rail arm. Okay? This is a side view. This is a 2-minute warning on an easterly read. In other words, that sun, with this type of digital protractor, if the sun is coming at you, you'll have a 2-minute warning before you get center mass. And that's what you want, center mass of the sun. Once you get center mass, you make sure you're level, click, and get your reading. Hey, I've got 51 degrees. What's my surface? Flat. I got a 51 degree reading. I'm over 45 degrees. I'm coming off a flat surface. I can't get 51 on the sphere. Geometrically impossible. Why? Line of parallel. Line of parallel, baby. You walked into the doorpost. You're driving a car looking the wrong direction with your seat reclined way back. You exceeded line of parallel. That's how line of parallel works. It is accountability and validation within these processes and applications. It is a reality. Let's talk about what we should have got in our education system, but we didn't. The 9-step geometric validation process. In other words, how do I determine the surface shape? What are the processes? We already talked about the equipment. That's step 1. Step 2, we want to verify the digital protractor for accuracy. Bump it against a manual protractor. You can either do it aiming, or you can write it on a board, draw an angle in, check your angle, or use a square. We want to verify the equipment is recording accurately. Step 3, determine OS position. The orientation position, observer location, inside or outside the prime meridian zone and the latitude. Step 4, elevation. We need to know that elevation must be recorded for effect. Step 5, OS survey the sun survey point and place it 90 degrees. All we're doing is transferring that survey point to our location. The sun's at 90 degrees. We do that with the Marx Device, a compass along. That becomes the line of what? Magnetic. The line of magnetic. Step 6, sun clock time. When do we test? 3 hours after sun survey time and 3 hours prior to sun survey time. So if my sun survey time is noon, 1200 hours, my first reading, a westerly reading, will be at 1500 or 3 p.m. in the afternoon. That's a westerly time I get my reading. The following morning at 09, I do my easterly reading. That tests the 45-degree sector. That is the 45-degree sector test. Timing is everything. It is critical. Step 7, the observer setup, prepare to conduct observation. We just went through that, showed you. Step 8, conduct it. We showed you what the sight picture for that looks like. Too easy. Step 9, record the information and take the station down. How easy is that, really? Yeah. Okay. Got it. It's a little different. Like I said, that gentleman out there is like, yeah, I've seen everything on flat Earth. Nah, you ain't seen this, dude. I guarantee you. All right? So, 9-step geometric validation process. Too easy. What are the factors that we need to understand in testing? Okay, these are critical. Timing, when to actually do the test. The OS, or the orienting station elevation. How that affects testing, the OS location, inside or outside the prime meridian zone, and then OS distance. And that has a lot to do with the location of the OS. This example of this test box, and this isn't to scale, this is just to show you. This is what a test box looks like, center mass inside the prime meridian zone. In other words, the Tropic of Cancer, equator, and the Tropic of Capricorn. So if you're doing it, you're going to have what? You're going to have higher sun angle because you're what? You're closer to the sun. You're in the prime meridian zone. Your test box. Now your test box can be here, it can be outside, it can be anywhere in the world. Anywhere, this test can be done anywhere in the world. We just need to know the effects, okay? Timing, the test box, when to start, when to stop. 3 hours, that tests the 45-degree sector. That's what you're testing, that portion of the sphere, that portion of the flat Earth model. We're testing the sector. 3, 4, 5. Let's look at elevation. What elevation? This is another thing that escapes heliocentrists, and this is another red flag on how you can tell that that grid system that the heliocentrists built was wrong because it didn't come off of sea level. In other words, when I talk about sea level, that is nearest the perfect geometric shape form. That is near sea level. You're closest to the actual geometric shape of that surface of that model, whether it's flat or you believe it's a sphere. Sea level is it. What's going to happen at sea level? Because you're at lower angle or lower altitude, you're going to get what? Higher sun angle. You get up about 1,500 feet, you're going to have what? Lower sun angle, higher elevation. So it's a reverse effect. The higher you go in elevation, the lower sun angle you're going to have. And at higher elevation or high altitude, above 5,000 feet, you're going to have the lowest sun angle. So guess what happens if you test your model at high altitude and it fails? Do you think it's going to pass going down to sea level? If you're failing at high altitude, it ain't going to get any better for you, because your angle is going to increase to the sun. The sun is the real answer. And this is what happens when distance, same thing, as we move farther out from the guide angle or the object, the elevated object, as we move away from it, what happens to our angles? They decrease. They go down. This is the effect of distance outside the prime meridian has the greatest effect. And this is kind of what the breakdown, what it looks like. This is inside the prime meridian zone, the Tropic of Cancer, equator, Tropic of Capricorn in the south. You're in the 90-degree zone. you're in that zone. You're in the highest elevation, sun elevation zone. The sun is always what? 90 degrees in the prime meridian zone, whether you believe on a flat earth or on a sphere. Once you understand that, this is extremely powerful, understanding that. Outside the prime meridian zone, you're going to have lower sun angle reading. Why? Distance, and then also elevation. If your station is at a higher elevation, your sun angle comes down. So those are the effects we need to understand. Let's talk about the military science of it all. Visual perspective. I know some of you, there have been some great experiments on visual perspective using the sun. I'm going to tie in military science because military science ties right in with visual perspective. Military sun and star shot, celestial survey, I'll talk a little bit about that. Weapons bore sighting really kind of brings it all together. Military science addresses atmospheric lensing and refraction. The sector range fan. In other words, we're going to use triangulation. Military science. The strategic and fundamental accuracy of military science is vital. Lives depend on its safe use and practice every day. And because second place in military science can get you conquered real quick. Understanding visual perspective. Many of you have seen the visual perspective. Look like looking down a hallway. If you're in a hotel or whatever and you're looking down one of those long hallways, you'll see that the sun at noon is right over top of us. We're at about 90 degrees or very high in the sky. Mid-afternoon, that starts to move away from us, and then the sunset, it moves linear. Okay? Moves linear. Opposite effect when you get in the morning. Now, what I want you to remember is remember this visual perspective outline, because I'm going to start to develop that through military science. I'm going to talk about the U.S. Marine Corps and the United States Army use M2 aiming circle, and this is what this device here is. It's a surveys device. It's to put artillery cannon pieces on the same or common line of direction, line of survey. Military uses it. It's called a M2 aiming circle. All right. In an artillery unit, we have a double check. In other words, you have a lay circle, primary aiming circle, and you have a safe circle. These circles are going to verify that you have the correct lay information. In other words, I want to be shooting the right way at the bad guys. I don't want to shoot at the good guys. So they're going to check. There is a double check verification within the system. That's why we use two circles. The safe circle will verify the lay circle is accurate. In this act, and I'll say it again, in this act, we can exclude atmospheric lensing and refraction. How? We can exclude it because in military, there are 360 degrees in a circle. The military artillery uses mils. In other words, there are 400 mils in a circle, 360-degree circle. They are more infinite. They are more defined. Why? Because we have to be very, very, very accurate. Because if we're not, we make a mistake, somebody dies. It's that simple. It is lethal. Again, accountability. What these two circles will do, one will use astrological survey, in other words, a sunshot. They will use a sunshot in the day or a star shot in the night. They will get their survey off of it. They will put an EOL, an end of orienting line, or a survey marker down. Once they set their survey in, the safe circle will come in and will go magnetic, grid magnetic, which is the same thing as going to what? Polaris, the North Star. Same thing. Going grid magnetic, they use alternate methods of lay. Once they do that, they will turn an angle on each other. You will face each other. And you will do what is called bumping. when you bump, in other words, when you're facing each other, I'm looking at you, you're looking at me, we have to be within 10 mils. Guess how wide 10 mils is? About that wide. Put 10 hairs together. We can now, 99% of the time, they will bump within 1 to 2 mils. In other words, from high angle down to 10 or 15 degrees, we can exclude atmospheric lensing and refraction. Military does it every day and night. In other words, when those folks at NASA tell you, well, that's due to atmospheric lensing and refraction, when we look up in the 2017 eclipse, I'm like, dude, you are so wrong. You are way out there. That's not what happens. There is very little, within about 1/8 of a degree. You may have some, but 99% of the time, you don't have any. Very minimal. The U.S. military does it day and night, and this is what I'm talking about. You're looking, I'll use the example, these circles, when you see these circles, they're like a ring. You read, the rule of thumb is you read from the outer ring into the middle. So if you see a number on the outside, you read that number into the middle. This example is 1/600. If you see red for the safe circle, you read red. So I read 1/600 to the safe circle. The safe circle has what? 1/600 back at me. We are 0 mils. That's how that works. Now I want you to remember when I talked about visual perspective, see how the walls and the floor and the ceiling all start to fill in. This is from Hasty Astro, from the U.S. military. We have our end-to-orient, we have our survey. This transfers to the gun line, then it transfers down to where we're shooting down range. We can exclude the atmospheric lensing and refraction. Now we start to fill in the what? The visual perspective. Look at the shapes and the form, the floor, the hallway, the walls all start to fill in with visual perspective. This is how I develop STO and SIMO. Timing. Now we have the ceiling, we're using the sun. The sun becomes the EOL, or the line of survey. We're just transferring it. It all works. Process, application, accountability, and validation. It all comes together. The visual perspective is there. It all fills in. Again, just showing you the lines of parallel. You have limits left and right. The keys STO or SIMO both work within this application and process. And this is the 45-degree sector test box. This is why it works. Same thing with weapons live fire ranges. They do the same thing. Visual perspective, geometry, you have left and right limits, visual perspective. That shape is in everything that military science does with regards to gunnery and weapons. Every time that I saw, when I did my research, heliocentrism tried to creep into military science identified it and made it a non-factor. In other words, we'll put it in there, but we're not going to use it. I'll give you the example. In this table, ATB 3-0922, this is a weapons range fan, left and right limit. You're 200 mils left, 200 mils right. That's your fan. That's what you can fire your weapon. U.S. artillery weapons. Anytime you go outside that, you have to physically shift the weapon. So what they did is, cleverly, they've put in, you add 1 mil for the Earth's curve beyond 300-400. Well, guess what? You're going outside the limit. You have to physically shift the weapon. That's where you're going to get your 1 to 10 mil displacement. So whoever did this, they were very clever. Very, very clever. And they did the same thing for beyond 3,000. You're outside that weapon's range. Of course you're going to shift. You're going to have the 1 to 10 mil displacement. And in every instance I found this, I found 2. Here's the other one. If it's important for artillery, it's on this table. It is on this table. And then look at standard conditions. This is used every time. Meteorological data, temperature, wind. I want you to look at gun target line position. In other words, the position of the cannon to the impact area. Look at number 3. What does it say? No rotation of the earth. This is a standard condition. In other words, hey, we identified you heliocentrist, however, we don't need you. It doesn't work. And then they listed the rotation of the earth down here as a non-standard condition. Guess when they use non-standard? Never. It's never used. Very clever again. Everything else is very important. If it's on there, it's critical. Atmospheric lensing and refraction exists at 10 to 15 degrees down to the ground. The heliocentrists know this, and they will use that against you when you conduct your experiments. That's why I said, go up and use the sun, man. That's the real answer. Weapons bore sighting, the same thing. You have line of parallel. You can exceed, if you look here on the right, you have lines of parallel, the cannon tube and then the weapon sight. You can exceed the line of parallel. You can't. Otherwise, you're instituting a lead. You can adjust the weapon sight in towards the cannon tube, but you cannot exceed the line of parallel. You are instituting a lead. When I talk to the military guys about that, that's when it clicks for me. I said, remember when you do weapons bore sighting? Line of parallel. And oh, dude, I forgot about that. Sector range fan, real quick. Again, if you're 1 degree off your line of survey at 46 degrees or a cumulative total of 91 degrees, you're over 1.5 million miles off line of survey. That's how far their grid pattern is off. References for these links, they're on the website. Operation Resolute Time, the breakdown, where it took place in Kabul, Afghanistan. I did it in 2000, 18 May to 7 August, one of the most extensive tests in recorded history. Over 81 tests, the globe model, outside, here's our test box, outside the prime meridian zone. I was 765 miles north in Kabul, Afghanistan, at a high altitude of 5,963 feet. High altitude. The globe model failed 57 of the 81 tests, or 70%. Think you're going to pass inside the prime meridian zone? You can't even pass the test outside and at high angle. We gave the globe model maximum major advantage of high altitude and outside the prime meridian zone, and it failed miserably. Again, we can calculate distance just by triangulation using a degree and the baseline distance at the Tropic of Cancer. We can figure the sun's distance, 3,500 miles from that position. I say the sun is between 3,000 and 4,000 miles. It's based on your position. What happens after sun angle, or their grid is off? The heliocentric, highly touted orbital mechanics does not work. In other words, when you see red, their orbital mechanics fails. In other words, you do not have the Earth rotating or spinning around a sun. It's not happening. Why? Your alignment's off. Dude, you're off by several million miles. In other words, you can't tell me that the sun is up here and your orbital mechanics work. It has to be down here. It has to be low angle. So that's why we do direct measurement, because that directly goes into orbital mechanics. Your positioning of these celestial bodies is out of alignment. You're out of alignment by several million miles off a line of survey. So your orbital mechanics goes into failure. So you're not orbiting around anything. You're stationary. Let me say that again, stationary. Where you see red, that's orbital failure. Orbital mechanics for the flat Earth, see any red on there? Just the prime meridian rings. It works, 90 degrees, no problem. Orbital mechanics on the flat Earth model works, too easy. I did Operation North Star. I started testing for the celestial body, the North Star. Again, off line of parallel from North Dakota at 46-degree parallel. We exceeded line of parallel by 3.2 degrees, or 334 billion, call it 335 billion miles off a line of survey. So not only the sun, the North Star. Let's talk about what we may live in, and I'm going to wrap this up. The enclosed system, projected objects, what we have within the system, or what we may live in, an enclosed world. Now, I know that all flat earthers don't believe that we live in an enclosed system. However, we can tie it all in the enclosed system if we look at the stars as a power grid. Now, some of these stars may actually be projected objects, but some of them may be crystals used within salt water and charge the system. So in other words, this is kind of like, almost like a septic system, running and flowing. The tides would regulate that. The tides are built in so they fill the water reservoir. This keeps this system running. It's kind of like a car battery for an engine. If you take, and like they did nuclear testing and they shot nuclear missiles up in the high altitude, if you fracture the firmament, you could potentially damage the power system. Now I looked at it and I was like, man, they're going to kill the system. If you fracture that, these stars may actually power the sun. And now it may not look like this, but this is just to give the idea that this object is drawing power. It is a power grid. And if you don't know about salt water and electricity, I encourage you to look at it, because it is real. And this is how you would operate that system. You use the salt water, you use crystals within the star field, you can run this system. You want it self-supportive. You don't want to have maintenance on it. But if you fracture the firmament, this sun starts to turn what? Red, brown, and then black. You just killed the power system. It's like taking a car battery and taking a drill and drilling into the car battery, and your car battery goes dead because all the fluid drains out. Same thing. And these objects are highly likely that they are projected. They are projected objects. Now, I wouldn't worry too much about shooting rockets and nuclear weapons up at the firmament. You can't get enough thrust at high altitude to get up there. And I think the creators knew this. Physics works against rockets at high altitude. You have no thrust or lift capability. And that's a design safety factor. Why? Because we as humans, we're pretty dangerous. We're very destructive. But again, you have a flow that could come right from the ocean, fills right up into our sky, and right back down. Cyclic. It's too easy. Summary, we talked about quite a bit. I know maybe, hopefully I didn't melt your brain, but hopefully I gave you some knowledge and an information share and gave you something to look at. Again, if you have questions about anything that I've talked to you about today, please just come up and talk to me. I'm very open, and I like talking about what we talked about here today. If you have questions, you can email me at CoreyIFish or visit the website. Thanks again. You've been a super crowd.